Imagine eating at a Michelin star restaurant every single day. You're sitting there marveling at the complex, world-class dishes,
Eating
right?
the best food imaginable.
Exactly. And never once realizing there's just one guy in the basement, literally working for free, chopping all the vegetables for the entire world. Welcome to the deep dive. Today, our mission is to pull back the curtain on the invisible, volunteer-built software machinery that powers, well, roughly 90% of all video on the internet.
It really is the ultimate unsung hero story of the digital age.
Yeah.
I mean, we're looking at open source projects like FFmpeg and the VLC media player.
Oh, VLC. Everyone knows that one.
Right, you've almost certainly seen VLC's iconic orange traffic cone logo. It has been downloaded over 6.5 billion times.
6.5 billion. That is just a staggering number.
It is. But what's truly mind-blowing is that these tools, which power the back ends of YouTube, Netflix, Chrome, and believe it or not, even the Mars rover, they are maintained by a tiny group of volunteers in their spare time.
That's wild. Using the internet without knowing about these tools is honestly like flying on an airplane and not knowing what an engine is. But before we can appreciate the genius of the people writing this software, we have to grasp the impossible physics problem they are actually solving here.
Yeah, the core issue.
Because raw digital video in its uncompressed state is simply too massive to exist on the internet.
It is a literal math bottleneck. Think about a standard 4K video for a second. You have a grid of over 8 million individual pixels on your screen.
Right.
And each pixel has a specific red, green, and blue value. If you want smooth video, you have to update that entire grid of 8 million pixels 60 times a second.
So that's just an ocean of data.
Exactly. If we tried to send that raw data over our current network infrastructure, the entire global internet would melt down instantly.
So video compression isn't just like zipping a text document, right? You don't just neatly package the data and unpack it perfectly later.
Not at all. To make video streamable, developers have to shrink the file size by a factor of 100, sometimes even 1,000.
Which means they have to systematically throw away massive amounts of information. And they do it without you, the viewer, ever noticing that anything is missing.
That's the magic. And to achieve that factor of 1,000, they don't rely entirely on computer science. They rely on human biology.
Okay, let's unpack this. Because that sounds like something out of a sci-fi novel. The software targets our biological blind spots.
It really does. It's a concept called psychovisual distortion. The software is specifically designed to exploit the evolutionary flaws in human perception.
Wow, how so?
Well, our eyes evolved to be incredibly sensitive to changes in brightness and contrast. So luminance, because that is how we detect edges, movement, and shadows in the real world.
Right, like spotting a predator in the bushes.
Exactly. But we are much less sensitive to fine details in color. So the very first trick these video codecs pull is to stop using RGB or red, green, blue.
So what do they use instead?
They shift the video into a mathematical format called YUV. And what this does is it separates the brightness of the image from the color data.
Oh, I see.
Once those are separated, the software secretly strips out up to 3/4 of the color resolution. The data size drops off a cliff immediately.
But the picture still looks fine to us.
Yeah, your brain fundamentally cannot perceive the missing color detail because the brightness remains sharp.
The biological trick is brilliant, but then there is the mathematical trick, right? Taking advantage of redundancy.
Of the spatial and temporal redundancy, yes.
Because if you have a locked-off camera shot of a person talking and there is a white cloud in the background, there is zero reason to redraw that exact same white cloud 60 times a second if it never moves.
Exactly. Instead of sending millions of pixels for a static background over and over, the software just sends a tiny microscopic note.
Just saying, like, keep this the same.
Yeah, the note basically says, for the top left corner, just reuse what I showed you in the last frame. And to pull this off, the video is chopped up into different types of frames.
Right, I read about this. You have iframes, which are basically your anchor points, right? Like complete high-quality still images.
Yes, exactly. Then you have p-frames, or predicted frames, which only contain the mathematical differences from the previous frame.
But then there's the third type, which totally broke my brain when I was looking through our sources. B-frames.
The bidirectional predicted frames.
Yeah. Wait, if I am understanding the mechanics of this right, the software uses B-frames to predict a frame based on a future frame that hasn't even happened yet.
That's right. It looks ahead.
Doesn't the video have to decode completely out of order to do that? Doesn't that inherently cause a massive lag?
You'd think so.
Yeah.
It absolutely relies on time travel logic inside the decoder. The decoding order inside your computer's memory is completely divorced from the display order you see on your screen.
Which sounds like a chaotic, broken way to play a movie.
It sounds messy,
Yeah.
but it is a highly orchestrated illusion. The media player downloads a future reference frame from the internet, decodes it silently in the background, and holds it in a temporary memory buffer.
Okay, so it just hides it away.
Right. And then it uses that future knowledge to flawlessly fill in the missing data of the frames you are watching right now. It completely separates the math of decoding from the timeline of reality.
That is just incredible.
And if we connect this to the bigger picture, this invisible buffering dance is the exact reason why a Netflix stream can absorb minor internet hiccups without constantly freezing up on you.
So the next time you watch a smooth, sweeping panning shot in a movie, just realize you aren't watching a real recording of reality. You are watching a highly optimized psychovisual illusion constantly predicting the future.
Beautifully said.
But executing that illusion requires an astonishing amount of compute power, right? Doing billions of time-bending predictions a second has to melt a standard processor.
Oh, it absolutely would if they were writing standard code.
Yeah.
But standard modern programming languages are actually too bloated to do this efficiently on a global scale.
Really, like, too much overhead.
Exactly. When you have billions of devices decoding AV1 or H.264 video nonstop, every single CPU cycle matters. So the developers of FFmpeg and VLC have to abandon modern coding conveniences entirely.
They drop down and speak directly to the raw metal of the computer using assembly language.
Right.
For context, most software today is written in higher-level human-readable languages like Python or C. You write the code, and then a program called a compiler translates your human logic into the microscopic machine code that the processor actually understands.
Yeah, that's the standard workflow.
But compilers have to make generalized, safe guesses. When you write an assembly, you are throwing away the compiler completely.
You are. You are manually writing the exact electrical instructions for the physical hardware.
And there's a specific technique they use for this, right? CMD.
Yes, CMD, single instruction, multiple data. In a standard language, you might tell the CPU to add 5 to the brightness of one pixel, then loop back and add 5 to the next pixel.
Which is pretty slow.
Extremely slow. With SIMD in assembly, a developer issues a single godlike command that alters 16 or 32 pixels simultaneously at the exact same clock cycle.
Wow.
And the scale of this is what truly staggers the mind. FFmpeg has over 100,000 lines of handwritten assembly code.
100,000 lines. Handwritten.
Yes. And a newer open source project called DAV1D, which is built specifically to decode the insanely complex AV1 video format that one has 240,000 lines of handwritten assembly.
Here's where it gets really interesting, though. We live in an era of AI vibe coding, where people are just talking to chatbots to generate apps. We have incredibly smart compilers and advanced memory-safe languages like Rust.
Oh, definitely. The landscape has changed.
So why on earth are human beings handwriting raw machine code like it is 1985? Can't the computer just optimize itself better than a human can?
What's fascinating here is that we have fundamentally hit the limits of Moore's law. Hardware is no longer magically doubling in speed every 2 years to cover up our sloppy, bloated code.
Right, we can't just rely on faster chips anymore.
Exactly. And compilers, no matter how smart, simply cannot match the ingenuity of a human expert who deeply understands the physical, spatial architecture of the CPU.
So the humans are still beating the machines at this level.
By a lot.
Yeah.
The handwritten assembly code in these media projects achieves speed improvements of 10 to 50 times over standard C code. In some specific architectural edge cases, it is 62 times faster.
62 times. That is the literal difference between a video stuttering to a halt and playing in flawless, buttery 4K.
Without a doubt, the developers writing this operate like fighter pilots. They are pushing the hardware beyond what the original designers at Intel or ARM even mapped out.
They adopt a true renegade hacker mentality from what I read.
Oh, completely. They routinely bypass the operating system's standard rules for how functions are supposed to talk to each other.
Just to save time.
Yeah, they invent their own custom calling conventions, just to shave off a few milliseconds. They will even hijack instructions explicitly meant for cryptography and repurpose them, just because that specific circuit pathway processes video pixels faster.
It is pure digital alchemy. But this level of raw, metal-touching expertise isn't just used for making modern streaming faster. They apply these exact same skills to literally resurrect dead technology.
Yes, the digital archaeology aspect of this community is astounding.
These developers go to incredible lengths to reverse engineer proprietary dead formats so that the internet doesn't lose its history, right?
Exactly. Take a legendary developer known as Kostya. He tackles the Sisyphean task of staring at obscure binary blobs.
Like, what kind of files are we talking about here?
He will take a 20-megabyte binary file from a forgotten 90s screen sharing software, like an early version of GoToMeeting, or maybe a custom codec used for a single 10-second video clip in a 1993 Star Wars game.
And just to be clear on how impossible this is, they do not have an instruction manual. They don't have the original source code. The companies that made these formats are dead and gone.
They're flying completely blind. To reverse engineer it, they run the old binary file in a virtual machine, attach a debugger, and pause the program at the CPU level.
Oh, wow. So they freeze it in time.
Yeah, and then they step through the computer's memory line by line, instruction by instruction. They literally watch how the hexadecimal memory registers change when a specific pixel turns red on the screen.
That sounds incredibly tedious.
It is. From that microscopic behavior, they have to reverse calculate the complex mathematical formulas the original creators used.
It's like an archaeologist trying to reconstruct an entire lost civilization's spoken language using nothing but a toothbrush and a single piece of broken pottery.
That is a perfect analogy. And their end goal isn't just to make the video somewhat playable. Their goal is bit exactness.
Bit exactness.
Yeah, they want their new reverse-engineered open-source code to produce the exact same microscopic digital footprint as the original proprietary software.
So if you have an old family home video lying around on a hard drive, or a weird email attachment from 2004 that miraculously still opens today, you owe a massive thank you to a volunteer in Europe who stared at raw machine code for months.
You really do.
Which brings up the most glaring contradiction in this entire ecosystem. You'd assume the people holding the fabric of the internet together are sitting in executive suites in Silicon Valley. But they are mostly working out of their bedrooms for free.
It is a brutal meritocracy. One of our sources pointed out a famous saying among the core developers. They say, "We don't care if you're a dog, we care if your code is excellent."
I love that.
It's true, though. You have 16-year-old teenagers writing world-class assembly code right alongside seasoned professionals.
But that...
Right. And when the developers politely asked for a long-term support contract to justify the labor, Microsoft allegedly offered a one-time payment of just a few $1,000s.
So what does this all mean for the future? Because I have to push back a little here on behalf of the tech giants. Trillion-dollar companies do rely on this code for actual real-world security.
So they do.
We've got global infrastructure built on this. Doesn't the open source community have a fundamental responsibility to keep the digital world safe? Especially when you look at incidents like the CIA's Vault 7 hack, where intelligence agencies created a modified, weaponized version of the VLC player to trick users and steal data.
Security is undeniably vital, but this raises an important question of scale and context. Applying Fort Knox-level corporate AI security bots to a hobbyist's padlock on a 30-year-old video game codec is fundamentally crying wolf.
It's a bit disproportionate, yeah.
In one instance, a corporate security bot flagged an issue as a severe 7.5 critical vulnerability. But when the volunteers finally dug into the code, it turned out the exploit just caused a single pixel on the screen to render the wrong color.
Are you kidding? A single pixel?
Seriously, just one pixel. When corporations demand urgent, high-stress-free labor for things like that, it leads directly to massive burnout among the very few maintainers actually keeping the internet running.
Which is dangerous in itself.
Very. That is exactly how we ended up with the recent XZUtils near miss, where an exhausted, solitary open-source maintainer eventually handed over the keys of his project to a malicious state actor simply because he was so overwhelmed by the relentless demands.
Wow. Despite that crushing pressure, though, the integrity of these creators is incredible. Jean-Baptiste, or JB, the president of the Videoland project behind VLC, was famously offered tens of millions of dollars over the years to bundle adware and tracking software into the VLC installer.
Oh yeah, he could have been insanely rich.
But he turned it all down. He walked away from life-changing generational wealth just to keep the project pure, fast, and completely ad-free for the public.
And that fierce independence is what allows them to keep pushing the boundaries.
Yeah.
Because their obsession with optimizing every single millisecond isn't just about preserving old movies or streaming YouTube anymore.
Right. It's evolving.
Exactly.
Yeah.
Today, this open source video technology is leaping off your computer screen and directly into the physical world.
This is where the tech crosses over into science fiction for me. JB has a new project called Kyber, and it moves the industry from passive video streaming into active teleoperation.
Yeah, we are talking about remote controlling drones, humanoid robots, and rovers over the internet.
Which sounds cool, but what's the challenge there?
Well, standard video streaming, like Netflix or a Twitch stream, has a built-in delay of 10 to 20 seconds because of that buffering illusion we talked about earlier.
Right, the B-frames and all that time travel logic.
Exactly.
Yeah.
But when you are operating a drone at 60 miles an hour, a 10-second delay means you've crashed into a wall before you even saw it on your screen.
Okay, yeah, that is a huge problem.
To fix this, Kyber abandons standard internet protocols and uses custom UDP protocols.
UDP basically prioritizes raw speed over perfect delivery, right? Because standard internet traffic waits around to make sure every single packet of data arrived flawlessly.
Yes, but UDP just blasts the data at you as fast as possible, not caring if a frame drops here or there, because waiting for a dropped frame means fatal lag.
And the staggering goal they are chasing with this is 4 milliseconds of glass-to-glass latency.
4 milliseconds. That means the camera lens on a robot in France captures an image, the hardware encodes it, blasts it across the ocean, decodes it, and displays it on a glass screen in Las Vegas in 4/1000ths of a second.
That is just incomprehensible speed.
It is. But to achieve that, they can't just optimize the video pipeline. They have to solve the nightmare of clock drift.
Let's explore that, because clock drift is wild. A modern robot isn't just a camera. It has 5 different cameras, stereo audio sensors, and tactile mechanical inputs on its fingers.
Every single one of those sensors has its own internal quartz clock. And in the physical world, no 2 clocks run at the exact same speed.
So they slowly fall out of sync.
Exactly. Over a few hours, the audio clock might drift slightly ahead of the video clock, which drifts slightly ahead of the mechanical sensor clock. Kyber has to act as the ultimate conductor, perfectly synchronizing the audio, video, and mechanical commands down to the microsecond.
Why is it so crucial that they are perfectly synced?
This is critical for AI. If an AI model is being trained on data from a remote-controlled robot, and the visual data hits the server a fraction of a millisecond after the tactile sensor feels a wall, the AI learns the wrong physics of the universe.
Oh, wow. It's the perfect analogy. FFmpeg used to act as the internet's memory, like preserving formats, archiving history, making sure old files didn't die. But now it is becoming the internet's central nervous system.
That's a great way to put it.
When you are remotely operating a robotic hand halfway across the world, a 4-millisecond reaction time is the exact biological difference between the robotic fingers catching a falling glass and closing a fraction too late, letting it shatter on the floor.
It really is the culmination of decades of unseen labor. I mean, the psychovisual tricks of early video compression laid the groundwork.
Right?
The raw poetry of handwriting assembly language provided the unparalleled speed. Surviving corporate demands preserved their independence. And now, these unsung wizards in their bedrooms are building the low-latency control systems for tomorrow's autonomous robots.
What a journey. So the next time you hit play on a video, jump on a video call, or watch a live drone feed, take just 1 second to appreciate it. You are crossing an invisible digital bridge, built pixel by pixel, line of assembly by line of assembly, by unpaid volunteers who literally built the modern world.
I want to leave you with one final thought to ponder, actually.
Okay, let's hear it.
Think about the very nature of video compression we discussed earlier. We have built the entire modern internet by systematically deleting the visual data that human eyes cannot see, utilizing psychovisual tricks just to save bandwidth.
Yeah, throwing away 3/4 of the color, like you said.
Right. But as we move into the future, we are increasingly using this highly compressed video to train vast AI models and autonomous robots to understand our world.
Oh, I see where you're going with this.
Are we accidentally blinding our future AI by training them on a version of reality where the subtle, invisible data has already been permanently erased by a codec?
Wow. If a robot is looking at the physical world through a mathematical algorithm originally designed to trick a human eyeball, what is it actually seeing?
Exactly.
That is a deep dive for another day. Thanks for joining us, and we'll catch you on the next one.